Hello, everyone. So last time we finished the topic of first order ODEs. Now this time we want to look at second order ODEs, basically higher order ODEs, and in particular, we'll look at second order ODEs. So chapter 2, a higher order ODEs. And let's start with second order ODEs. So basically a second order ODE, we know it looks like this equation, the general form. Let's say we have a of x times y double prime plus b of x y prime plus c of x y equals d of x. So highest derivative appeared is the second derivative. And these functions a of x, b of x, c of x, and d of x are arbitrary functions of x. So basically we can divide everything by a of x to make sure that the leading coefficient or coefficient of y double prime is 1. So that's normally a convenient assumption if we can assume that the highest coefficient is 1. So similarly in the algebraic equations, if we have a function or a polynomial, if we divide by the leading coefficient, let's say we have an equation and we divide both sides by the leading coefficient, and then we can assume the leading coefficient is 1, and that would make the calculations generally a little bit simpler. So here also, if we divide both sides by the leading coefficient, which is a of x, then the leading coefficient becomes 1. So let's divide both sides by a of x. Which is, by the way, non-zero. Note that we can assume that a of x is non-zero, because repeatedly we have said in this course that if we divide both sides by a function, we have to make sure that that function is non-zero first. Why can we assume that this function is non-zero? Well, what happens if it's 0? If a of x is 0, then your first term will be 0. It will vanish the first term, and then you'll be left with a first order ODE. But right now, we're assuming that you have a second order ODE, right? Because first order ODE, we dealt with it in the first chapter. And right now we want to look at the topic of second order ODE. So that's why we can assume that a of x is non-zero. So let me write down y here, but I just told you the reason. That if it's 0, then we don't have second order ODE, we'll have first order ODE, and we already studied first order ODE before. Now, if we divide both sides by a of x, then what do we get? Then we get y double prime plus b of x over a of x times y prime plus c of x over a of x times y equals d of x over a of x. So we can assume that a second order ODE is of the form y double prime plus p of x times y prime plus q of x times y equals f of x. if I call this term b of x over a of x, let's call it p of x. This term c of x over a of x, let's call it q of x. And this term, let's call it f of x. And in that case, we'll have an equation of this form. So we can assume that the general form of a second order ODE is an equation of this form. So this is a general form. And in the special case of this general form, if f of x is 0, so previously we have mentioned that if you have an ODE where the right hand side is 0, then that ODE is called homogeneous equation. So if this function is 0, f of x is 0, then we can say that we have a homogeneous second order ODE. If f of x is 0, then the ODE, then this ODE will be called homogeneous. Similarly, of course, this definition can be applied for higher order ODEs as well. For example, if you have a third order ODE where the right hand side is 0, your function where there is no y in it is 0, then that's called third order homogeneous ODE. And similarly for higher orders. So homogeneous ODE then, or second order homogeneous ODE, will be of the form a second order homogeneous ODE will be of the form y double prime plus p of x times y prime plus q of x times y equals 0. Okay, the goal is to, now the goal in this section is to find the general solution of a second order ODE of a given second order ODE. Okay, let's start with the theorem that, so this is our final goal, is to find the general solution of a second order ODE, or if you have an initial value problem, then we want to find a unique solution in that case. But if the initial values are not given, then we need a general solution. Well, general solution will include the constants versus initial value problem will not include any constants. You will just have a unique solution for it. So theorem here, suppose that y1 and y2 are the solutions for y double prime plus p of x times y prime plus q of x times y equals 0. Then any function of the form c1 y1 plus c2 y2 will be also a solution for this ODE. For this ODE, I mean this ODE that is given here. So let's say we have a homogeneous ODE. This is a homogeneous ODE because right-hand side is 0. And let's assume we have two solutions for it. So y1 is a function, y2 is also a function. And once we have two solutions for this ODE, so still I haven't explained how we can get two solutions, but let's assume for the moment that we have two solutions, we have access to two solutions of this ODE, then any function of the form C1 y1 plus C2 y2 will be also a solution for this ODE. And C1 and C2 here are arbitrary constants. Here, C1 and C2 are constants. So in other words, we can say that any linear combination of y1 and y2 are solution or is a solution for this ODE. C1 y1 plus C2 y2 if C1 and C2 are constants is called a linear combination of y1 and y2. So this is a concept that you learn in Math 252 linear algebra. Okay, now since you may have taken Math 252 a few semesters ago, or even if you have taken one semester ago, maybe I have forgot some concepts. So for this reason, let me remind you about some of the important concepts in Math 252 that we will need both in this chapter and more importantly in the next chapter. The next chapter we will use more concepts from Math 252 compared to this chapter. So let me give you some reminders. From Math 252. So let V be a vector space. Be a vector space. Well, you learn about the concept of vector space in Math 252. You know that each vector space, basically it's a set equipped with two operations called addition and scalar multiplication, which satisfy some axioms. And the most standard example of vector space is R2, R3, R4, right? But those are not the only vector spaces in the world. There are other vector spaces as well, such as the set of, for example, continuous functions or set of polynomials. Those are vector spaces as well. Now, if you have a vector space, and let's say, let V1 and V2, let's say small v1 and small v2 be vectors. Vector means elements of this vector space. Elements of this vector space. Then we can say that any vector of the form C1 V1 plus C2 V2, where C1 and C2 are constants, is called a linear combination. A linear combination of V1 and V2. So a linear combination of V1 and V2 means a vector of the form C1 V1 plus C2 V2, where C1 and C2 are constants. So for example, if V is equal to, let's say, R2, and let's say V1 is equal to 2 and 3, and let's say V2 is equal to 1 and 4. See here, I have a vector space, R2, the set of all vectors where each coordinate is a real number, or the set of all pairs where each coordinate is a real number, and equate with standard addition and standard scalar multiplication. Now I am considering two vectors inside R2. Now any vector of the form C1 V1 plus C2 V2 will be called a linear combination of V1 and V2. So then we can say that, for example, 2 times V1 plus 3 times V2, which is 2 times 2 and 3 plus 3 times 1 and 4. And we can simplify this as 4 and 6 plus 3 and 12, and that's 7 and 18, is a linear combination of V1 and V2. Or another linear combination. So there are infinitely many linear combinations for V1 and V2, because see, a linear combination is of the form C1 V1 plus C2 V2, but C1 and C2 are arbitrary constants. I can take them to be 2 and 3 like this example, or I can take them to be, I don't know, 5 and 4, or 6 and -1, whatever I want. So, or another linear combination of V1, V2 is basically, let's say, V1 minus V2, which is 2 and 3 minus 1 and 4, and that's 1 and -1. So this is the concept of linear combination. But like I said, your vector space doesn't have to be R2 or R3 or R4. It could be the set of, for example, continuous functions, or set of differentiable functions, or set of polynomials. So, as another example, let's say let V equals the set of all continuous functions. And let V1 equals sine x, V2 equals cos x, then V equals, let's say, 2 sine x plus 3 cos x is a linear combination of V1 and V2. Two sine x plus 3 cos x. See here, if V is a set of all continuous functions, then if that's my vector space, then the vectors by definition are elements of the vector space. Now, sine x is an element of this set because sine x is a continuous function. Cos x is also a continuous function, so sine x and cos x are both elements of this vector space. Elements of a vector space are called vectors. Vectors of that vector space. So V1 and V2 are vectors in V, and then V equals 2 sine x plus 3 cos x is another vector because it's another element of this vector space, because 2 sine x plus 3 cos x is also a continuous function. So this is also a vector in this vector space. And this is a linear combination of V1 and V2. Why? Because anything of the form C1 V1 plus C2 V2 is called a linear combination. Here my C1 is 2, my C2 is 3. So 2 sine x plus 3 cos x is a new function which is written as a linear combination of these two vectors, sine x and cos x. Okay, now about another important concept you learn in Math 252, linear independence. So again, let V be a vector space. And let V1 to Vn be vectors in V. So these vectors, V1 to Vn, are called linearly independent. Linearly independent if the only solution of C1 V1 plus C2 V2 plus Cn Vn equals 0 is the trivial solution C1 equals C2 equals Cn equals 0. Otherwise, i.e., if there exists at least one non-trivial solution for C1 V1 plus Cn Vn equals 0, then V1 to Vn are called linearly dependent. So linearly independent means the only solution of this system is C1 equals Cn equals 0. See, when I say the only solution, I mean solution for C1 to Cn. So let's assume V1 to Vn are fixed. So we have some fixed vectors that are given. And let's say we want to find the solutions for this system, C1 to Cn, C1 V1 plus to Cn Vn equals 0. The solutions for C1 to Cn. What solutions do we have for C1 to Cn? One solution is always C1 to Cn equals 0. Of course, if you set all C1 to Cn equals 0, if you set all of these guys to be 0, then left-hand side becomes 0, and you will have a solution. Because 0 times V1 plus 0 times V2 plus 0 times Vn is 0. So if you set all these Ci's equals 0, then you will have a solution for this. But the question is that the only solution for this system? Or there are other solutions as well? If this is the only solution for this system, then the vectors V1 to Vn are called linearly independent. And If not, if there are other solutions, then they're called linearly dependent. So you also learned in Math 252 that whenever you have a linear system can have no solution or one solution or infinitely many solutions. So it is not possible, for example, that a linear system has two solutions. That's not possible. Or three solutions. That's not possible. If it has more than one solution, then it has infinitely many solutions. So if it has exactly one solution, then they are called linearly independent. If more than one solution, which by another theorem, you know that it would mean that you have infinitely many solutions. In that case, they're called linearly dependent. So for example, if V is R2, let's say, and let's say V1 equals 1 and 2, V2 equals 2 and 4, then we can say that V1, V2 are linearly independent. Sorry, linearly dependent. Why are they linearly dependent? So let's find all solutions for C1 V1 plus C2 V2 equals 0. So this is what we need, the system that we need to solve. C1 V1 plus all the way to Cn Vn equals 0. Find all solutions for C1 to Cn. When we say solution, we mean solution for C1 to Cn. So find all solutions for C1 and C2 in this case. Let's see whether there is only trivial solution or there are other solutions. And as we said, in that case, it would mean infinitely many solutions. But let's see whether trivial solution is the only solution for this system. Let's find out. So C1 V1 plus C2 V2 equals 0. V1 is 1 and 2. V2 is 2 and 4. So then we can say C1 times 1 and 2 plus C2 times 2 and 4 equals 0. And that gives C1 plus 2C2 equals 0. 2C1 plus 4C2 equals 0. So from the first equation, this means C1 equals minus 2C2. And this one also means C1 equals minus 2C2. Because it's 2C1, if I take 4C2 to the other side, then divide by 2, again, I'll get C1 equals minus 2C2. So basically, I have one equation with two unknowns. So there are infinitely many solutions for this system. So that means any vector or any C1, C2 with C1 equals minus 2C2 is a solution for this system. For example, C1, we could say C1 equals, or C2 equals 1. Then C1 would be minus 2. Or let's say if you set C2 to be 2, C1 would be minus 4, and so on. So there are infinitely many solutions. Infinitely many solutions for C1, C2. So that means V1, V2 above are linearly dependent. So we showed that this system, C1, V1 plus C2, V2 equals 0, has infinitely many solutions for C1 and C2. For example, if C2 is 1, C1 minus 2, or C2 is 2, C1 minus 4, and so on. So this system has infinitely many solutions for C1 and C2, which means that these vectors are linearly dependent. Or another example, let's say again, if we have V equals R2, and let's say V1 equals 2 and 1, V3 equals, and say V2 equals 5 and 3. So this time we can check that V1 and V2 are linearly independent this time. So again, the beginning is like before. You have to start with C1, V1 plus C2, V2 equals 0. Again, you will have two equations with two unknowns. Then C1, your unknowns are C1 and C2. This time you will see that the system has only the trivial solution C1 equals C2 equals 0. And then that means the vectors are linearly independent. V1 and V2 are linearly independent. Or another example, let's say if V equals R3, V1 equals 1, 2, 1, V2 equals 2, 1, 4, and V3 equals 3, 3, 5. Then V1, V2, V3 are linearly dependent this time. Why are they linearly dependent? But again, of course, one way to show this is to start with C1, V1 plus C2, V2 plus C3, V3 equals 0, and show that you have infinitely many solutions for C1, C2, C3. That's one way to do it. But for this specific example, it's also possible to guess a solution for C1, C2, C3. Because if we can find at least one non-trivial solution for C1, C2, C3. By non-trivial solution, we mean a solution where at least one of C1 or C2 or C3 are non-zero. If we can find at least one non-trivial solution, then that means that the vectors are linearly dependent. So we can guess basically, we can find all solutions. That's one way, but we can guess, it's easier to guess at least one non-trivial solution for this specific example. So note that. So I want to guess some C1, C2, C3, where C1, V1 plus C2, V2 plus C3, V3 becomes 0. So let's add V1 and V2. So V1 is 1, 2, 1 plus V2, which is 2, 1, 4. Now this one, if I add, then I'll get 3, and this will be 3, and this will be 5. 3, 3, 5. So I just need to add minus V3 to this, and then I'll get 0 vector. So minus 3, 3, 5, and then this is 0, 0, 0. This plus this minus this gives me 0. So that means V1, V2, V3. Are linearly dependent. So here we showed C1 equals 1, C2 equals 1, C3 equals -1 is a non-trivial solution for C1 V1 plus C2 V2 plus C3 V3 equals 0. we guess the solution for this because we set C1 to be 1, C2 to be 1, C3 to be minus 1. Then we found out that V1 plus V2 minus V3 is 0. So that means this is a non-trivial solution for this system. The moment that we verify that this system has a non-trivial solution, then we can immediately conclude that V1, V2, V3 are linearly dependent. So as an exercise, we can, of course, find all solutions for C1, V1 plus C2, V2 plus C3, V3 equals 0. And you will see that this is one of the solutions, but there are infinitely many solutions for this system in this example. So these vectors are linearly dependent. Another example, let's say V equals the set of all continuous functions. And let's say V1 equals sine squared x. V2 equals cos squared x. V3 equals 1. So when we say V3 equals 1, because this vector, this should be an element of this set. So this should be a continuous function. And when we say V3 equals 1, we mean as a constant function. 1 as a constant function is, of course, a continuous function. And cos squared x is also a continuous function, and sine squared x is a continuous function. So these are elements of this set. Now, these three vectors are linearly dependent. How can I show that they are linearly dependent? So to show this, we need to show that C1 V1 plus C2 V2 plus C3 V3 equals 0 has a non-trivial solution. As a non-trivial solution for C1, C2, C3, meaning that C1 sine squared x plus C2 cos squared x plus C3 times 1 equals 0 as a non-trivial solution for C1, C2, C3. So when we say this is equal to 0, we mean constant function 0. Previously, when we had, for example, C1 V1 plus C2 V2 plus C3 equals 0, this 0 meant vector 0. Vector 0, 0, 0. Why? Because our vector space was R3. So 0 in this vector space means vector 0, which is 0, 0, 0. But in this example, our vector space is the set of continuous functions. What is the 0 of this vector space? The 0 of this vector space is constant function 0. So when we say something equals 0, we mean equals constant function 0. So we are looking for C1, C2, C3, where this linear combination equals constant function 0. Equals constant function 0 means this has to be 0 for every x. So let me explain here. So this equality must be valid for every x. Why should it be valid for every x? Because this 0 means constant function 0, and if a function equals constant function 0, that would happen only if left-hand side is equal to 0 for every value of x. So let's guess. Let's guess a solution for this equality or equation. Let's guess a solution for equation above. So C1, C2, C3 must be constant. For example, 1 or 2 or 0, something like that. So can you guess a solution for this, a non-trivial solution? Of course, trivial solution is always a solution. Trivial solution means if all of them are 0. If C1 is 0, C2 is 0, C3 is 0, then 0 plus 0 plus 0, of course, will be 0. So that's always a solution. But the question is whether we have non-trivial solution, a solution where at least one of the CIs is non-zero. Well, here if I set C1 to be 1, C2 to be 1 as well, then C sine squared plus cos squared, it will be 1. So if I set C3 to be minus 1, then I'll have 1 minus 1, which is 0. So set C1 equals C2 equals 1, C3 equals minus 1. Then we will have 1 times sine squared x plus 1 times cos squared x minus 1 times 1, and that is 0 for every x. So that means v1 equals sine squared x, v2 equals cos squared x, and v3 equals 1 are linearly dependent. We found out that if we set C1 to be 1, C2 to be 1, C3 to be minus 1, then C1 V1 plus C2 V2 plus C3 V3 is 0 for every x, meaning the left-hand side is equal to constant function 0. So that means our vectors are linearly dependent.